Okay, in this video I'm going to look at a situation where I'm solving for the concentrations at equilibrium, and I'm going to use the 100 rule, and I'm just going to show that without too much effort I can do a little bit better than what the assumption of the 100 rule predicts in this situation. So here's my equilibrium. I have nitrogen dioxide, it's a gas, there are two of them combining with oxygens to form nitrogen dioxide, two of them. And I'm giving myself an equilibrium constant here of 1.8 times 10 to the negative 3, and an initial concentration of 0.2 molar of each of my reactants, and none of my product. So that's my initial concentrations. And just to check for the 100 rule, I have to show that my concentration of my reactants over K is greater than 100. Now I want this number to be as big as possible. In here, I've set it up so that my number works out to 111. It's good enough to use the 100 rule, right? 111 is greater than 100, but I specifically made it near the border, so this isn't going to be that great of an assumption when we do this at first. So here my change, I'm going to be reducing by 2x here, reducing by x, and creating 2x of this. And so at equilibrium, 0.2 minus 2x, 0.2 minus x, and I'll end up with 2x. And then, because I've met my need for my 100 rule, what I'm going to say is that the change in the concentration of my reactants is small, and as a result, I can ignore it, and so basically I'm going to neglect this 2x and this x. So my K expression then, products, NO2 squared, because there's 2. This shouldn't be NO2, this should just be, that's my problem. That should be nitrogen monoxide. If this reaction looked weird, that's why it's nitrogen monoxide forming nitrogen dioxide. So nitrogen monoxide, still 2 of them, and oxygen. Okay, so this was 1.8 times 10 to the negative 3. And this is 2x squared. And this is going to be 0.2. It would mean 0.2 minus 2x squared, but because I met this guideline, I don't have to put in the 2x. And 0.2. Alright, so 1.8 exponent negative 3 times 0.2 cubed, effectively. I get 1.44 times 10 to the negative 5. 4x squared. So I can just jump here. X is going to be 0.0018. Actually 19. Now, this actually turned out to be pretty good. 0.2, so the concentration, the worst one will be nitrogen monoxide, which would have been 0.2 minus 2 times this x, which is 0.2 minus 2 times 0.0019. Which works out to 0.196, which really isn't very bad. 0.2 is approximately equal to 0.196, so this turned out to be a pretty good approximation in the first place. The concentration of O2, which would mean 0.2 minus x, works out to 0.198, which again is very close to 0.2, so it's a pretty good approximation. And then my final concentration of nitrogen dioxide being 2x would have worked out to be 0.0019 times 2, or 0.0038. Molarity. But let's say for some reason we want it to be really, really accurate. How could we get this to be even more accurate? Well, basically we could repeat the process. So now we could assume that our initial concentrations of nitrogen monoxide and oxygen and nitrogen dioxide were the things that are given here. So this one will be 0.0038, and this one will be 0.198, and this one will be 0.196. And now, because I'm closer to equilibrium, these changes, this minus 2x and this minus x, and this formation of 2x, will be even smaller than they would have been in the first case. So basically, I was at 0.2. I assume no change, and what I found out is that I moved a little bit to 0.1, let's say 98. So now I'm here, and I'm even closer to what my actual equilibrium would have been if I hadn't made any assumption at all. So now, if this was a small assumption to say that's not a change, now we have this very small assumption to say that there's no change, and so these x's are really ignorable. And at equilibrium, we can get a better estimation by using the starting values, because now our changes are very small. It's still a pretty simple k expression to solve for. The k value is, 1.8 times 10 to the negative 3. And now I'm going to have the concentration of my nitrogen dioxide squared over the concentration of my nitrogen monoxide squared and the concentration of my oxygen. Inserting these values or expressions accordingly. I'm going to take the bottom numbers and the left number and combine them all into one number, and then I'll be able to square root this to make the solving of it easier. So this just ends up being 1.369 times 10 to the negative 5. And now I'm going to square root both sides. And I get 3.7 times 10 to the negative 3 is equal to 0.0038 plus 2x. So I'm going to bring the 0.0038 over to the other side. And I get 1 times 10 to the negative 4 essentially. Negative. And then I'll divide by 2. And I get x is down to negative 0.0005. Remember when I was discussing what I did here, I assumed that I jumped most of the way to the equilibrium, but that I hadn't quite got there. Now I see that I actually put my x in the wrong direction. X turned out to be negative, which means the equilibrium is going to shift in the other direction. So what that really means is in my first assumption, I started here, that was my initial, and I jumped all the way to here. I jumped just past the equilibrium a little bit, and now I'm correcting back to it a little bit. So my final concentrations then of nitrogen monoxide, oxygen, and nitrogen dioxide are, so I said it would have been 0.196 minus 2x, and this one would have been, so that's going to be 0.1961. So here I assumed that this would be the concentration at equilibrium, and this is the actual concentration at equilibrium. We can see how in my first assumption with the 100 rule, I went from 0.2 to 0.196, and it's pretty close, but it is a little different. Now, my change is so small that all I'm going from is 0.196 to 0.1961, and we can see that the difference between these numbers is only 0.0001, and that's a very, very small difference. And so we can see that by repeating the 100 rule, my assumption of the 100 rule that my concentration of my reactants not changing became even better. My concentration of my oxygen would work out to 0.19805, so even a smaller change in that situation. So this is a very, very good assumption now. And my new concentration of nitrogen dioxide would have been 0.0038 plus 2x, which works out to, in this case, 0.0037. And so it's a minor change, but by repeating this process, I'm getting closer and closer to the exact solution, or a solution that leaves me with no assumption or no discrepancy between what I assume the concentrations of the reactant to be and what they actually were when they completed at equilibrium. So in this case, the 100 rule worked pretty well in the first place. This is pretty close to 0.2, but this video shows how if you basically repeat the process, your assumption becomes even better. So the 100 rule can be used a few times. If the original 100 rule hadn't worked out so well, perhaps using the 100 rule a couple of times will allow you to get a change in reactant concentration that you consider to be small enough that you would consider the 100 rule to have been successful. So that's how you can do that using the 100 rule.